how images can get very quickly complicated. Yeah, so let's start. And I apologize, and please point me out when you see that my spelling is horrible. So we're going to be using, oh, sorry. Better? Yeah. Cool. So we're going to be plotting. Press that, sorry. So import that plotlib and numpy. And then a lot of what we're going to be doing is with image. I don't know how people say it. image. So let's load some example data from Skimage. Oh, sorry. How do you delete empty cells? D? Cool. Good. Yeah, so these are other imaging packages that are really good. I personally have never used Mahota's, but OpenCV is a really big one. It's really commonly used in computer vision. Skimage, I think, is really good for, like, you know, science, I guess, but they're both all good. Okay, so let's import an image. We're going to call it camera, and it's in the Skimage package under data.camera. Let's see what it looks like. So the way that images are held is in a NumPy array. So if you're importing an image and you want to see what it looks like, it will just be the raw pixel values of that image. So that's what you're seeing here. This is the array of the image, and it's 8-bit. So if you actually want to see, oh yeah, so you can see this. If you do type camera, I can show you that the reason that it doesn't look like a picture is because it's an array. So if you want it to, and you can see the shape of your image. So it's a 512 by 512 image. So that's how many pixels are in your image. But if we actually want to see what this picture looks like, that's when we move to matplotlib, show. And let's put it in grayscale. Did I spell that right? Oh, sorry. Yeah. Yep. And that's what our picture looks like. So if we want to pull out some simple statistics, if you have any questions, like, let me know. So let's print shape. And this is a bit of indexing. So we're feeding it the shape of the rows. I don't remember if it's rows or columns first. That's the 0. And then the shape of the other index of the other axis. We also want to take a look at the total number of pixels. Forgetting my commas. So there's also the range of the pixels, which is how dark is your darkest pixel and how bright is your brightest pixel. And you call that with the min and the max. And lastly, what is the average pixel intensity of the whole image? Thank you. And then you can take the mean of all the pixels. Of course, there's an error. It's not callable. Any help? Oh. It's collecting this information and putting it into this placeholder, the %d. So image shape as array. So like everything in the quotes in the red is just the text print, and then it's shoving into this %d, wherever there's %d, the item that was called here. So camera.shape of the 0 index is going here, so that's 512. So for instance, if like it's 512 and 512 is the same number, but if your image was like 512 by 64, those numbers would be different depending on what the arrays are, or yeah, what the axes are. And same for the rest of them.
What about the last one, 0.2f? Is that like 0.2 times or something like that?
Camera mean.
2 after the floating points. So that defines how many floating points you have after these positions.
Okay.
And before.
So that was stock data, a picture that came with Skimage. But we can also load our own images. So I have downloaded, and it's in the folder that this Jupyter notebook is running on, the image that was in the, I don't know, like page. Yeah. And we can import our own images. So it's a picture of a colony, can't spell. So similar to before, we're going to plot this figure. And when you print the shape of this image, now there's 3 numbers. So the first is the X and the Y, so that's how many pixels you have. But then the third is the color. So this image is a color image and it has 3 colors, red, green, and blue. And then a combination of that red, green, and blue gives you all the colors that like a mixture of those ratios gives you all the various colors. So that's typically the way that image is stored. Color is stored in an image is just 3 values, and then ratios of those values is what gives you the variation in the colors. So let's plot this picture. I cannot spell. So for our first plot, I'm plotting all the channels. So to tell it to plot all the channels, I'm indexing all. So what I'm doing here is telling it which part of the image I want it to show. And by having 3 semicolons, I'm saying take all of the image. So take all of X and Y, all of X, all of Y, and all 3 color channels. And then let me do a title. I'm really bad at labeling my. And then you'll see how this image is different when we only plot 1 channel. So same here. Channel. And I'll put the plot in a different place. And then now instead of taking all 3 channels, we're only taking the first channel. So by convention, it's RGB, so we're only taking the red channel. And let's see what we get. We get an error. This is how I code. Figure. Yes, it is. There you go. Yeah, so what you're seeing here is, do you guys still need the code? Just scroll up. But I'll speak about the image. So what you're seeing here is like, even though it looks like a gray image, it's not a grayscale image because even colors of gray are represented as a ratio and a mixture of red, green, and blue. So your 3-channel image, regardless of like even like a black image can be a 3-channel image. It just means it has really low intensity values. And then what you're seeing in the 1-channel image is what components of that grayish image are made up by red. And then just because it's not actually red, it's taking that red ratio value and applying like a different color scape on it. Yeah.
What's the number in the subplot, parentheses? What does that signify?
I'm pretty sure it's telling you where to put the plot. Yeah. So it's correct me if I'm wrong, but it's like put 1 plot here, row 1, like column 1, and the other plot here.
Yeah, it says split the figure into 1 row and 2 columns and plot it in each column.
Yeah.
first number.
Yeah.
So one row, two columns, then the first subplot you have one and the third.
And yeah, and then put this plot here. Yeah. Not plot lib. Can I scroll down? So yeah, this is what you get. So I'm not really sure how by default Skimmage chooses it's called an LUT, a lookup table, which is how it maps your intensity value to the actual color that it displays. So even though it's the first channel, which is red, it doesn't display as red intensity values. It really, this idea of like red as a color doesn't really matter. It's just holding an intensity value in the space. And then how it represents that intensity value, it can be in various different lookup tables. And yeah. Image manipulation. So now we can do more indexing and access specific pixels within these images and set them to whatever value we would like. Yeah. So here we're going to get the pixel value. I'm trying to word this, of the pixel in row 10 and column 10. And we do this by indexing. So we already had camera, but we're resetting it in case we did anything weird to it. And then again, with these square brackets, we can say, give me the value of the pixel in this position, row 10, and column 10. And it's 157. Just as a note, when we first said what type, like what's the type of this image, it was 8-bit, so integer 8, which means that the color space is represented from numbers from 0 to 255. And I always get this mixed up, but I'm pretty sure 0 is black and 255 is white. And if you swap those values, that would be inverting it. We'll get to that. So that we told it to tell us what is that pixel value, but we can also change the pixel values. So again, we access this pixel at row 3, column 10, and we say make it equal to 0. So 0 being black in this color scale. And let's show this. So you can you see that one black pixel up at the top? It's there. There. Yeah. No? No? And then similarly, you can ask it to reset an entire row so this is all indexing. So this is saying that for the first index, take the entirety of that index, so all rows, for the first 10 columns, and then set that equal to 0. You can see I have a black bar at the top. And then similarly, if you swap this around, it would be the first 10 columns that go black, because you'd be saying take the first 10 entries in the rows, and then all of the columns, and set those to black. So we can also ask it to find all of the black pixels. So like find all the pixels that are below a certain value and set those to a different, you're basically binning, you're saying what pixels are below this threshold and set those to white. So we're adding a mask, so it's a threshold is true. So I'm reloading. So previously we were writing over our camera array. So I'm reloading it so that we don't have the black stripe at the top. That's our fresh picture. And then we're saying we're gonna have a mask on our camera array where the pixels are less than 87, which means so pixels between 0 and 87, to us, we consider them black, but technically they are black. True black is 0, and then very, very, very dark grays. So that's what we're saying by setting a mask of 87, this threshold. And then we're applying the mask. And we're setting those values to 255, which are white, which is the highest end of the spectrum, which is white. You can see here, it found all of, do you want the code still? It found all of the black and like very dark gray pixels and set them to white. Good. So we were looking at that image in grayscale. So now let's see how it is when we were working with the 3-color space. So let's import this cat image. It's a stock image in the package. It's called Chelsea. And again, let's get a handle on what type of image this is. Something that is also doesn't come up in Skimmage is like the ordering of your channels, which can play a big role when you have like high dimensional images. Because like sometimes you'll have X, Y, Z, like C for color, and then T for time, and those can all be swapped around sometimes. So when you do, when you print the shape, we know that if it's these large picture values and then some value of like a low value of 3 or something, that's the color channel. But sometimes you might not know that if, you know, your picture is 3 pixels by 3 pixels, which doesn't often happen. But that's something to keep note of, is where these axes are stored in your NumPy array. Yeah, it's so this is what I'm talking about. We know that the first 2 are X and Y, and the third one is color, but sometimes we don't. So if things are looking weird when you're doing image processing, just maybe check that you're accessing the channel that you think you're accessing. So we can choose a pixel similarly and set it to green instead of just some intensity value from in a grayscale image. Now we're telling it to be a specific color, and it's RGB, red, green, blue is the common nomenclature. Let's pick a pixel, let's say 50 and 70, and set it equal to, we're saying we have, make that pixel have 0 red, be fully green, and have 0 blue. So in this, we're setting the ratio of the colors, which will lead to like a truly green pixel. And then we're not telling it to be in grayscale because we want to see the color. We see the green pixel? Where did I put it? 50, 70, somewhere over here. I don't see it, but it's there, trust me. Do you see it?
Few of them, we have a lot of them. 50 to 60, 70.
There we go. So it's there. And then similarly, we can apply a mask and set that mask to a specific color. Pixels to red. So we have our cat. Let's see. And then, so now instead of everything we're doing before, we were manipulating the image and storing it back in our original image name, but now we're not. So like, let's create a new array called red cat. And it'll be equal to, let's just copy cat. And then apply set our mask, our reddish mask, I guess. But saying for all X and Y in this color space, the 0 being red. So it's like all pixels that are pretty red. Like it's saying reddish is identifying all pixels that are red above a threshold of 160. So pretty red, reddish. And then similarly, we're applying the mask reddish. And we're setting all of the reddish pixels to the maximum value of red, which is 255. And then in those pixels, we're saying don't have any green and then don't have any blue. I want to see red cat.
I have a question.
Yeah.
So you mentioned that it's like red, green, blue, but then the 0 is in the blue section, isn't it? Talking about the reddish.
Okay. Yeah. So here we're indexing our image. So when we printed cat shape, like the shape of our image, what was it? It was X, Y, and then color, right? So over here, what we're indexing is our image. So we're taking with the semicolon, we're saying take all of the X values, all of the Y, but only the first instance of the color, which is red. So like the shape of cat is X, Y, and then color has 3 values, right? So how we were like, in this space, we would be we're pointing to specific pixel locations. And then in this space, we're pointing to a color channel. So here we're talking about the shape of cat, whereas here we're talking about the values that we want to set the mask of reddish to. That makes sense.
And anything that is like on the red channel, if that's for terminology, above the value of 160, it becomes like the reddish mask, and then you set all of those to the maximum value of red.
Yeah, 255. But you could also take, so the next thing is you can also, for like, if I set this to 0 and this to 255, I'm accessing the same reddish pixels that are above this threshold of 160, because we're saying, look in this color space and tell me which pixels, this like reddish is the mask, look in this color space and tell me which pixels are above 160. But now instead of setting them to totally red, I set them to totally green. And then similarly, you can also invert this color. So same thing, applying, well, now we're not applying a mask. Sorry, I was just looking at the code. You can do something similar. Instead of applying a mask, you are not adjusting any specific pixel value within the image, but you're just completely inverting the values. And I'll show you how to do that. So let's start with our cat. There's a note in this lesson that it's an inverted image. You're automatically going to recognize it as an inverted, well, not an inverted image, but like a distorted image. But the reason that one would want to do that is in Skimmage, it's RGB, whereas in OpenCV, the common nomenclature is BRG. So if you just automatically imported an image from Skimmage into OpenCV, the colors would be skewed. But it's easy enough to switch. So let's start with our cat. And then our BRG cat is just equal to our cat. And again, we're saying, give me all of the X pixels, all of the Y pixels. But now for color, instead of setting BRG cat to like the same color space, you're inverting it. And that's what that does. And got a bluish cat now. So that's what that does. It's saying take all the channel and flip it. So then you can also invert it. So everything we were doing before was playing with the color space. So we are accessing this last axis of the cat image and playing around with that, applying a mask and changing the color of it. But we can actually invert, so like change the scale of our 0 to 255 image and flip it. So now all 255 are 0, and it's flipped. And everyone has seen an inverted image, but that's actually what inverting that image is doing.
What's the double color? What does that mean for indexing in Python?
I'm not sure. Like, this is the way that you flip that. Yeah. So for instance, if it wasn't color like RGB, but it was like numbers 1 through 10, if you put the same thing, it would just flip it. So 10 is now your first in the 9, 8, blah, blah, blah. So that's the nomenclature for flipping it, or the syntax for flipping your. And I don't know it offhand, but you can also look up, for instance, like with similar indexing, if you wanted to only, like if you had 0 through 10 and you only wanted to flip like 5 through 10, you could say like only access like the last 5 ones and flip those. So it's all part of indexing NumPy arrays. So if we want to invert, I think it's also called a complementary image. Complement. We can do that as well with a different function. So from skimage, we want to import util invert cat is equal to util invert, and then we feed it the image we want. Did we overwrite cat somewhere? No. The inverted cat. So we didn't need an index. So like everything we were doing with color before, we were actually accessing specific pixel values above or below a certain threshold, where this one is just inverting all the values in the array, or in the array, in the intensity values in the array.
What's the difference between this one and the previous one? That one changed all the colors from like red, blue, green to the other way.
Mm-hmm.
This one, intensity and color.
Yeah, so intensity, so here, color is a ratio, like seeing this bluish cat, the blue cat instead of a red cat, that is because the image was a specific ratio of colors. It's a specific ratio of red, green, and blue. And here you're swapping that ratio. You're keeping the ratio of green the same, but you're swapping the ratio of red and blue because you're changing around the color space, right? But that, you can see that the relative intensities, like the blackest parts of the image are still black and the whitest parts of the images are still white, because you didn't actually play with the value that was stored within that image. The value being the intensity, the pixel intensity. So here, that's what you're doing. So now the color space is the same, but you're playing with the intensity. So where it was very, very red is now, instead of before where it was red, it's now blue. Here, where it was red, it's now the opposite of red. It's like where it was a high value of red, it is now a low value of red. And where it was a high value of green, it's now a low value of green. So you're actually playing with the data that's in your image as opposed to swapping around the ratios. So it's a difference between the ratio of the colors versus the actual intensity of each of the colors. And you can also convert from RGB to gray and from gray to RGB with another function. RGB. I knew that was going to happen. Gray cat RGB. Okay. Oh. I can't import it. Yes, it is. And it's not a Canadian color. And now we have a gray cat. So this one is interesting. So we were working with an 8-bit image, so all the values from 0 to 255. But depending on functions that you're using, they might require a certain type of input. So it's important, like for instance, when I'm doing something and I get a really weird plot or a really weird value, typically because I fed it it wasn't expecting this data type. But when you're playing with the values within your image, you can distort the image intensities, especially if the information in your image is coming from the contrast between the pixels. So there's a bunch of functions to allow you to change between these data types while maintaining that information within your images. And there's more here. I missed some. Yeah, so there's some functions in Skimage that allows you to change between image types while not distorting these values. Image as float and image as view. And I want to show you this. So you can see these are there's other data types, but these are typical ranges for images. So a really common image is called 8-bit, where the depth of your color is encoded by numbers from 0 to 255. So most images are 8-bit. If you want, so when someone's talking about the bit of an image, so a 16-bit means that you have a lot more depth in your color. So the variation from 0 to black in 8-bit is only encoded by 255 steps, whereas in 16-bit is much more, 32-bit is much more. But yeah, depending on the math that you're doing and the things that you're doing with your image, it might be more convenient to have it as a float. And then similarly, you can have 8-bit, 16-bit, and 32-bit, but instead of from 0 to the value centered around 0. So that's sort of 8-bit, 16-bit, 32-bit is sort of talking about the depth of information within your image. Yep. So same image, just different different data type. Do you want more code? I don't know. So we can also rescale intensities. So let's import that. So what we want to do here is stretch the, like we can, if an image isn't using the full range of the pixels, 0 to 255, we can stretch it and rescale it. So the min and max of this cat image is 0 to 231. So if it's an 8-bit image, we're not using the full color space because the maximum pixel value is not 255. But we can rescale this. And you can see that this has not yet been rescaled. It has the same min and max. So we can rescale it. And stretch the space. So instead of 0 to 255, it's 0 to 2 to the power of 10. 2 to the power of 10. And we can see what this looks. Oh, you can see what this looks like. And it's a much dimmer image. So we're like I was saying before, how in an 8-bit image you have. I actually don't know what this is. Obviously a lower depth value for your image. It's the full scale is not 0 to 255, and that's why it appears dimmer. So like I was saying before, with a 16-bit image, there's a lot more depth in that image. In this one, you're losing that contrast. So that information in those pixels. So when we're trying to choose thresholds and we're like trying to find interesting parts of our image, sometimes it's not best to be actually looking at an image. We actually want to plot histograms of our pixel values. So then if we're plotting histograms of our pixel values, we can identify peaks within our images that might be some interesting result and that we can target with a threshold. So to do this, we want to display histograms of our images. So let's import that camera image again. And plot a histogram. And Ravel, what that does is instead of it chugging through your image as an array, it takes all of your pixel values and just like flattens them out. So it makes it a lot easier and faster, really fast, to plot your histogram, which is really good when you have like really, really large images that have like X, Y, Z, 3 colors and time and things like that. Is that it? Yeah. So if you remember the camera image that we had before, and if you remember when we applied the mask and we said, take the black and the really gray values and set them to white, and it targeted the man's coat, you can see here that this peak is that black coat. And this is what, some medium gray. So this is your color scale from 0 to 255. And there's a lot of black, like black or very dark gray pixels. And then this is a lot of sort of medium gray pixels, but there's not many very, very white pixels. So that's another way of, when you look at a picture, like I look at so many images for my work that I don't actually see pictures anymore. I mostly see histograms. Because when you're trying to target a specific region of your image, or when you're thinking about how could I play with the features of this image, this is the way that the computer sees it, a bunch of pixel values. And when you're applying masks like that, this is sort of how you would target a specific area.
How do you index those pixels? Like, this is not an XY format, it's like one number associated with this pixel.
Yeah.
How would you index them?
You could print out, like, I mean, like you could take that mask and you could print out the coordinates of those pixels if you wanted to. But that's exactly what, like, for the sake of plotting the histogram quickly, that's what Ravel does. Like, you are losing that information, the spatial information, for the sake of the pixel count. But like, there are other more complicated algorithms that keep the spatial information, and that's actually one of the really challenging things in image analysis, is like, how do you define these features and relate it back to like time coordinate or space coordinate, and then what does that mean, right? Translating like a dynamic feature. I work in videos, a dynamic feature into like something biologically relevant or, you know, meaningful to us, but only working with space, pixel, like contrast, so pixel value, and then time if you're working with videos. So that's sort of like intro into like decomposing a picture into like seeing pictures as just pixel values and histograms. So then for image segmentation, we do something a little bit more interesting, but it's working around like really grasping that everything we're working with is just based on pixel values and their contrast, and some of the segmentation is again using the spatial information of the pixels to apply the segmentation or to apply the watershed. So let's import that colony one. Colony equals we have our colony, and if you remember, it's X, Y, Z and color. And we can plot a histogram of it. I'm going to copy the code from up here. Let's make it a grayscale image. So now we have an array that is our colony, but converted to a grayscale image. And then we can plot this histogram. You can see the nature of, you can see the nature of this image is different. There are a lot of background pixels. So all of this, like the sharp peak in the dark gray, dark black, I think are these background pixels. And then there's many fewer pixels that are white, which represent the colonies. Good. With that code. So we can threshold this image. And it's identifying. So it's showing you one value for all of these darker pixels and then another value for this bump. So so it's sometimes not intuitive what all the peaks are representing within your image, but with the threshold you can see where in your image are these peaks. So I didn't put it in here, but we're going to use the canny edge detector. So this is an algorithm detector to detect the edges of these images. So it's an algorithm that is using the spatial information of the image to identify high contrast regions and calling them an edge. And you can get this algorithm from Skimage. Import. So if we want to find the edges, just apply this algorithm. And then it'll find the edges of the image, and we can fill in the detected objects with a fill. NDI binary fill not defined. I don't know what I need to import. Let's carry on.
Usage D and G in edges.
There we go. Told you it was all about the spelling. No, this is not defined. Yeah. I can still. There we go. Cool. Solved. I did read that. I was like, I didn't import SciPy anywhere here. I wonder if that's going to come up. Yeah, so it's 7:15. So if anyone wants to like head out, it's fine. We're going to go over. So like that was all the basics of images and color, space, and indexing. And you can dig more. Like that's like the nature of how we store images in NumPy arrays and then indexing. And then this stuff is more, it's like sort of going over examples of algorithms that you can apply. But yeah, the algorithms that you would be using for like on your image is very specific to the questions that you want to ask. So we're going to go over the canny edge detector and then the watershed algorithm, which is another algorithm to do segmentation. So these are two different ways to detect edges and then segment your image. So the rationale behind that is that you have all of these pixels, and first you need to classify like what is background, what is foreground. It's this idea of like breaking up your image based on the pixel values in some smart way to then be able to act on those pixels, on those subsets of pixels in some special way, as opposed to simply doing a threshold, because sometimes a simple threshold is not sufficient for how you want to parse out this different parts of your image. So yeah, if you need to leave. Yeah, so let's plot these two images, the image edges and then when the edges have been filled in. So we're going to plot a figure of fig size. So I'll keep the code up. Yeah, you can see that. So in the first one, when we're plotting the edges, this is what the canny algorithm does. So it's detecting, it was implemented in the 70s. There's a whole bunch of math that says why it works. But it is using your pixel values and the spatial relationship of those pixels to detect edges. So that's what you're getting back to, is it's not exactly answering a question about where those pixels are, but yeah, the spatial information of your pixel values is really important for extracting features. And then once these edges are detected, you can then fill solid circles. So you can see here that some of the colonies where, let's say they were a smaller colony or a less bright colony, so that's biologically relevant because it's not as strong of a signal, they weren't fully filled in. And that's because the edge didn't make a full enclosed object to then be filled. And we can apply this edge detector on the cat. We're applying the canny filter on our cat image, and we're applying it to all X, all Y, and the first channel. Not sure why we're dividing it by 255. I think we're making it, we're like normalizing it by the total value. So now it's a decimal. Oh, this is what I was talking about. So this is an example of the canny function wants a value between 0 and 1. So we're normalizing the entire image by 255. But this is an example of maybe you want to convert, like depending on your image, maybe you want to convert it to a float or another one so that you're not distorting your image or like inherently changing the ratio of the values, like depending on what like for instance, if you have really small, if you're applying an algorithm where really small values like shoot up to infinity or something like that, maybe you don't want to just normalize it in this way. It's just something to be aware of. And then we can also fill in areas that have a full enclosed object. I'm gonna copy the code. Plot it.
Plot the,
Pardon?
filtered image first.
Pardon?
Can we plot the filtered image first? We check the output can.
Yeah, of the cat. Yes. Yeah.
ing edges.
Am I misspelling something? What? Pardon? So you can see there's a lot less filled in spaces in the cat, but it is detecting the edges. That's what you want to see, right? Yeah.
Is that why you divided it by 255 with a decimal to make even 255 flow instead of like a whole season is flow?
It's so if we, let's see what happens if we take it out. Not much. But my guesstimate would be this canny function. There, yeah, I did. Yeah. It could just be a safe measure. Like Neil, the woman who left, wrote this, so it could just be like it could just be by practice when you know that a lot of skimmage functions take are expecting a 0 to 1 value, but you know all of your images are 0 to 255. By default, you can do that. For me, by default, like the first thing I do is convert my images to the data type that I want. Different ways of doing it. But this would be like, for instance, if I did delete this and ran it the first time and like the edge detector was just so wrong, my first guess would be like, is it expecting what I think it's expecting? So that was the canny edge detector. So there's also the watershed algorithm, and this is the last bit. So it's also a segmentation algorithm, but it operates in a little bit of a different way. So let's import it. So Sobel is another segmentation algorithm, not similar, well, like segmentation in the way that canny is also segmentation. Skimmage dot. So first we're going to make an elevation map. And that's what Sobel does. So it looks similar to the canny edge detector, right? And it is in that it's a algorithm that is like meant to detect these edges, but it's actually it's plotting peaks, like peaks, and then like areas in your image where there's high contrast, meaning areas where the highest values, so like the whitest values, drop off rapidly to black. So that's or where there isn't, so like where it is that background, it stays black, but then also in the center of the colonies, it's also black, because that area is also not an area of like high contrast because it's all white. Does that make sense? It's another algorithm. And then the next step is separating your pixels into classes. Here we're separating it into 3 classes. And then we're going to use these classes to define markers. And we're doing 3 classes, but it could be 2 classes, like binary, black and white, foreground and background. So we're going to have markers. So we're creating an array of zeros, 0 values. And it's going to be, that's not how you spell zeros. And it's going to be like the image, so in the shape of the image that we have. And then we're setting the marker array equal to the image values that are less than 0.35. Set those equal to 1, so our marker being 1. And then markers that are above 0.55, set those equal to 2. And then we can show our markers. You can see that here. So in this image, we have, we created a new array called markers, and we made it in the shape of our image. And then we plotted in one marker, yellow, all the ones that are below 0.35. So that's probably black. And then there's the middle class that's between 0.35 and 0.55. And then into the above class that's above 0.55. And that corresponds to like the dark blue, the greeny blue, and then the yellow. And then we can use our Sobel edge detection and our markers to segment it in with the watershed algorithm or the watershed transform. So set segmentation, water elevation, markers. So here have our segmentation. We're calling this watershed function, and we're feeding it the elevation map that was made with the Sobel and our markers. And then for where marker equals 1, so that was the background pixels that were below the 0.35 threshold, we're setting those equal to 0. And then you have the remainder of our markers, the foreground ones, filled in inside of the watershed. So for example, you can see in this method of segmentation, the colonies that didn't form a perfect circle I'll scroll up. The colonies that didn't form a perfect circle when we're doing canny segmentation are filled in because we filled it in by applying these markers into our elevation map. So one of the reasons why it's important to have these colonies filled in appropriately is because because if you remember in the canny edge detection, the ones that didn't make a full circle weren't filled in, which means it won't be classified as an object. So what we can do also is now label each of these segmented objects as individual objects. So this is all isolating features of our images to then do something downstream. So we can label objects. Label. Colony number. So here, so you can imagine if, for example, if you're doing really high throughput analysis, like let's say each of these dots was a colony that was growing under a specific condition, and you want to know like how effective this treatment is, you don't want to sit there counting colonies or measuring colony sizes. So in this way, you can run all of, and like let's say you have 500 images, you could run all of your images through this pipeline, and then for each one of your images, you can tell me, it can spit out how many colonies are actually found on that image. And you know, obviously, if you set up the experiment that you have like 36 by 48 colonies, so you know how many colonies, like the efficiency of your colony growth in this treatment. And then this is also, it's showing you each color. So this is an example of color ratios. And here the color ratios are representing a different unique object. So it is in sort of this like graded rainbow fashion, but if you actually looked into this color representation, it is a unique label for each object. And then, I mean, looking at this image for me, you could also ask how big are my colonies? So if you wanted to know like how many pixels across each of your colonies are, that would be asking what's the diameter of each of my colonies, which will also be a readout for colony growth. So this is sort of the way that if you want to get biologically relevant features or just relevant to you features out of your images, that you start thinking. It's all about pixels. That's it.
Does anyone have any questions or let's just take one for the
Thank you.
We have our shiny apps lesson. So that's just interactive plumbing art and how to make those apps that you can post online and serve on the document server. So easily. Yeah, I think